In this video, we're going to look at the use of integration to find areas of regions. Now, that needs to be explained a little bit carefully because what the integral produces is the area between the curve and the horizontal axis. And it gives us the value of that area, the signed value of that area. So the integral is the signed value of the area. And what that means is regions above the horizontal axis, the variable with which we're integrating with respect to, will give us a positive signed value for the integral. Areas below the horizontal axis, such as area 1 here, will give us a negative value, a negative signed value for the integral. We need to be very careful about that. So when we integrate some function, some rational polynomial, rational function in this case, we need to check where it intercepts the horizontal axis. Because if we're integrating regions below the horizontal axis, they will give us a negative sign value for the integral. If we then integrate a region that's above the horizontal axis, that will give us a positive value. If we then add those together, the negative part will cancel out the positive part. And for instance, if you were to integrate y equals sine x between 0 and 2 pi, what you'll find is that the integral of that will give you, looking for space, sine it, the definite integral, 0 to 2 pi, will give you 0. Now that's clearly not true because there's area here. The total area, if we're looking for the area between the curve and the horizontal axis, it's not 0. Okay, the signed value of the integral is 0. That's correct. That is true. Okay, but the total area is not. And we need to be very careful because the region below the horizontal axis gives us a negative signed value for the integral, and the area above will give us a positive value. If we add those two together, we'll cancel out and get 0. So it's a nonsensical answer. So we need to be careful. We must find the intercepts. We must find where the integrand, if we sketch or plot the integrand, where does it cross the horizontal axis? And we must treat the two regions separately. Regions above the horizontal axis, such as area 2 in this example here, will give us a positive value. And it must be treated separately to the integral for the region of area 1 in this particular case. For this example, that's the area from 0 to 2, which is below. Okay, we must be very careful about that. So we need to find out where our function crosses the horizontal axis in some interval that we're interested in integrating between. So we want the area between the curve, and the horizontal axis between x equals 0 and x equals 6. But it crosses at x equals 2. And hopefully my sketch is reasonably accurate in showing that. So this area below, the signed value of the integral will be negative. Now, of course, area can't be negative, so we need to correct that. And this is where the absolute value comes in. Now, what we can do is we can take our integrand here and express it as in partial fraction form. It has a repeated linear factor underneath. So what we need for x minus 2 over x plus 2 all squared is a on x plus 2 plus b on x plus 2 all squared. A and b are constants. When we work those out, we find that a is 1 and b is negative 4. Okay, so we put that in there. And we're now going to integrate. Now, again, we found that the result from 0 to 2 will give us a negative value for the integral, and from 2 to 6 will give us a positive value. So we need to treat those two separately. You must be very, very careful about that. Find the intercepts. Intercept or intercepts. Otherwise, you'll end up with a nonsensical result, and you may not realize you've got one. For instance, if you just integrate this rational polynomial here from 0 to 6, you get something like negative 0.11. Okay? Clearly not right. Okay? So, let's have a look. Let's take our integral here, 0 to 6, of 1 on x plus 2 minus 4 on x plus 2 all squared, integrated with respect to x. And we'll treat the first part, the bit below the horizontal axis, that's from 0 to 2, as we will take the absolute value of the result. So the absolute value of the evaluated integral. That is going to give us a negative value, the integral in this region, and we will take the absolute value of it because we are interested in the area. We've been asked to find the area between the curve and the x-axis. Okay, and if you're doing multiple integrals, that's in more than 2 or more dimensions, then for each of the same axes, everything I'm saying here applies. All right, let's integrate now from 2 to 6. That's the part of the rational function that's above the horizontal axis, 2 to 6, and we don't need the absolute value sign for that. We'll produce a positive result. Okay, so if we evaluate those, well, 1 on x plus 2 is easy to integrate. It becomes the natural log of x plus 2. Then we have minus 4 times. If we integrate this now, we just take x plus 2 upstairs if you like. So for instance, if I just write x plus 2 to the power of negative 2, and then if I want to find the antiderivative of that, it will end up being, raise this, minus 1, okay, on x plus 2, okay. It just simply raises the minus 2 by 1, so divide by 1, divide by negative 1, you get minus 1, and then 1 over x plus 2. So we put that in here, okay. Then we're going to evaluate between terminals 0 to 2. We'll do that shortly. We keep the absolute value sign outside. Same over here. Now we're going to integrate this between the terminals 2 to 6. Again, natural log of x plus 2 plus 4 on x plus 2. Okay, now we evaluate between the terminals. I'll put x equals 2 in here for the whole thing. Okay, minus x equals 0 in there. Same here, put in x equals 6, and then over here x equals 2. Okay, as we evaluate that down, we end up natural log of 4 minus the natural log of 2 minus 1. Okay, keep the absolute modulus sign outside. Don't lose track of that. Absolute value signs. Plus here, natural log of 8 minus natural log of 4 minus a half here. Okay, and a half minus 1 gives us minus a half. Natural log of 8 minus natural log of 4. Okay, here, using the log laws, we can have natural log of 4 over 2. Okay, we can condense that, simplify it, minus 1 plus, same over here, natural log 8 over 4 minus a half. So this gives us the natural log of 2 minus 1 plus natural log of 2, okay, minus a half. We're just going to play a little bit of games here. We can simplify this a little bit, but if we take out here, inside the absolute value sign, if we take out a factor of negative 1, so we're just rearranging this, so minus 1 in parentheses 1 minus natural log of 2 plus a natural log of 2 minus a half. Okay, if we take out the factor of minus 1, and then what we're having here is that this object here, the minus 1, we can then take the absolute value of that times the absolute value of that. We're allowed to do that as an inequality here. We know that this is equal to or less than this. And so absolute value of minus 1 is just 1. So we don't need to write that anymore. And with the absolute value of 1 minus log 2 plus log 2 minus a half. Okay, keep going here. Now we can write 1 as a natural log of e minus log 2. Okay, plus log 2 minus a half. That's the natural log of e on 2. Okay, the absolute value of natural log of e on 2. Now that's a positive quantity there. So it'll be equal to just the natural log of e on 2 without the absolute value sign, because this is a positive quantity. And the absolute value of a positive quantity is just a positive quantity. Plus natural log of 2 minus a half. Okay, again, what we will now do is, having freed ourselves of the modulus sign, we have the natural log of e on 2 plus natural log of 2 minus a half. Well, we can again use the log laws and rewrite that as natural log of e minus the natural log of 2, but then we already have here plus the natural log of 2, so those two can cancel out, minus a half. Natural log of e is 1 minus a half, gives us a half units squared. Okay, now the point of this video is not the log laws and all these interactions here. It's to warn you that the integral of an expression must take into account the intercepts where it crosses the horizontal axis, because the integral will give you the signed value of the region concerned. Regions above the horizontal axis will give you a positive value. Regions below the horizontal axis will give you a negative value. And if you are not careful, and if you blindly integrate, in this case between 0 and 6, then the negative part will cancel out some of the positive part, in fact more of it, and you'll end up with this particular integral with an answer of approximately negative 0.11, which is clearly not the case. Okay, we need to be careful. You need to take account of any intercepts, find where in the interval between the terminals of integration you need to find whether or not the function concerned or the integrand concerned crosses the horizontal axis. Very, very important. Not just blowing the integrate away. And for those parts below the horizontal axis, you'll need to put absolute modular signs around them. So you need to split up the integral into that part below the axis and that part or parts that are above the x-axis for this particular case, or whatever horizontal axis you're dealing with for the particular problem. You need to be very careful. The integral gives you the signed value of the area. You need to be careful because some of that will be negative if it's below the horizontal axis, and some will be positive. So just watch out for that, and that's it.